All right, the purpose of this last video of this lesson is to go over an AP style type question that involves doing some kind of differential equation application. So this is modeled very closely after a real problem. This isn't exactly a real problem, but it's very, very close to one. So basically I want to show the application of the differential equation and how they employ that. And then usually they tie in other concepts from other parts of the course. So this problem's modeled to show you not only the differential equation application, but also some of the other things they could ask that tie in previous things from the course. So first, let's get a handle on what the example's about. It's not the best example in the world. It's about amount of waste in a landfill at a plant in a landfill. But let's get a handle on everything that's going on. So first off, they tell us that a landfill has 1,200 tons of waste at the start of the problem. They tell us that there's a function W. W represents the amount of tons of waste at this landfill plant at time t. The rate at which the waste increases is given by a differential equation that they give us. So remember, rate is a signal for a derivative. Basically, dw dt is the change of waste over the change in time. And that's actually based on the amount of waste. So it's similar to what we were doing before, where the rate of change is based on the amount of waste that's already at the plant. And another thing to keep in mind is that these models usually don't last forever, as in they're valid for over a certain domain, and a lot of times after a certain point, they no longer work. So it's not uncommon for the AP exam to place a domain on here, a restriction. They basically say that this scenario is only valid for the first 20 years, from time 0 to time 20. This happens in real life, even if you go back to the first video where I was talking about the coronavirus. Those exponential models work, but they won't work forever because there's not an infinite amount of people who can get infected. Once a large enough number of people get infected, the exponential growth wouldn't be valid anymore. So when people make these models, you have to be careful that the model may not last forever. The conditions have to keep up for the model to continue. So they're telling us that this is only good for the first 20 years. So it's a technicality, but it's important to note sometimes because they sometimes reference that. And then they just tell us, t is in years, and it's most sensible to use time 0 as now. All right, so there are 3 questions. The first one is straightforward. It basically is asking us to solve that differential equation. W is the amount of waste, but we don't have W in terms of t. So we don't have W by itself and represented as a bunch of t's. So we want to find the function W in terms of t, and we want to use it to find the amount of waste after 2 years. So overall, we need to take that differential equation and solve it. When we solve it, we'll get W equals something t, and we'll be able to use it to get how much waste there is after 2 years. Now, I have the work on the back board. I ran out of space because I tried to cram A and B together. So the actual numerical answer isn't given, but I get to the point where we get the function, and all we got to do is plug in 2. So I'll show you the answer out of the calculator. Part B then ties in something from a previous topic in the course, basically using a tangent line approximation. Remember, a tangent line approximation is used to get a value that's nearby the starting value. So they want the tangent approximation at 0. They want us to use that to find the amount of trash present after 3 months. Now, kind of a strange question because we'll actually have the waste function. So we could have just plugged in 3 months, which is a quarter of a year, into the waste function, but they want to test concepts. So instead of using the waste function, they want us to use the tangent line approximation. A quarter year is not that far from 0. So remember, if we're close, the tangent line approximation should be pretty close to the real value. It's not going to be exact, but it'll be close. All right, so we'll go over that. And then the last part once again, tests something from previous in the course. It wants us to find the second derivative. Remember, d squared w over dt squared is that Leibniz way of saying we want the second derivative of w with respect to t. So we have the first derivative, so we just need to take the derivative of that derivative, and we can get the second derivative. That part's not too bad, but then there's this sort of strange question afterwards, because once we have the second derivative, they want us to use that information about the second derivative to see if the approximation from part B is an overestimate or an underestimate. Now, the tangent line approximation isn't exact, so it's either too big or too small, hopefully by a small amount, but it is going to be off. Now, we could use the original function to see if it's an overestimate or underestimate, but what's kind of interesting is we actually don't need the original values at all. Just the information about the second derivative can be used to figure this out. So I'll show you how to connect the information that we find about the second derivative to answer the question about our tangent line approximation. All right, so 3 questions. I have A and B on the board behind, and then I have C on its own separate board. So when I show you the board behind, A is on the left side, B is on the right side. So even though they're both up, I'll talk about the left side first, and then we'll move back to part B. All right, so part A is finding the function w. It's basically solving the differential equation and then plugging the value at the end. So to start, I just made sure I defined the terms on here so we know w is the amount of waste at any given time, and t measures the time in years. Now, they gave me the differential equation, so the rate of change of waste over time is based on the amount of waste and gets calculated in this manner. So we just need to solve this differential equation to get what w is. To get what w is, I need to solve this separable equation. So the way we solve a separable differential equation is we get the w's together, so I divide over the w's, and then I multiplied over the dt. So I got all the w's on one side, and then the dt on the other side with that number. Now, the only somewhat annoying technicality in here is that in order to integrate the left side, it's technically a function of a function. It's not 1 over w, it's 1 over w minus 300, so it's a little more complicated. So to do that, I showed a u substitution. It's not a difficult u substitution. The answer comes out as, if you've been following these, what you'd think it would be, natural log. But technically, we should show it to be proper, so I did. I made the w minus 300 simpler by calling it u. So if u is w minus 300, then du is the derivative of this. Derivative of w is 1 dw, and the derivative of 300, or negative 300, is 0. So the u substitution is pretty easy because dw gets replaced by du, and w minus 300 gets replaced by u. So then I get the integral of 1 over u du. Now that's clean, so that's easy to do. 1 over u's antiderivative is natural log of absolute value of u, and then 0.04 dt is asking me for the antiderivative with respect to t. That comes out 0.04 t plus c. Now, I don't want to leave things in terms of u. I want to go back to w and talk about the amount of waste. So I put the u replaced back with the w. So the u is w minus 300. Now, I go on to get the function w by itself. A couple things I do is, number one, I get rid of the absolute value bars in the next step. The reason for that is the amount of waste is minimum 1,200. Remember, it starts off with 1,200 units of waste, and the amount of waste, it says in the problem, is on the increase. So what that means for this quantity, w minus 300, is the smallest w ever is from the 0 to 20 domain is 1,200. 1,200 minus 300 is 900. This inner piece is never going to be less than 900, because basically as the waste goes up, it's going to get bigger than 900. Since 900 and numbers bigger than it are positive, I don't need the absolute value bar on this domain. So once again, I get rid of the absolute value bar and just make this natural log of w minus 300. And then to get rid of the natural log, we do the little thing with e. It's e to this power equals what's inside the natural log. So all of that is written here. I also use the trick where I get the plus c out of the exponent. So if you've been following the other videos, e to the 0.04t plus c is the same as multiplying by e to the c. So I get e to the 0.04t times e to the c. E to the c is just another constant. E is a number and c is a number. So they just call e to the c another constant, c, and throw it out front. Then I add it over the 300. So if you solve that, you get it as w by itself. I get w equals c e to the 0.04t plus 300. Now I want to know what c is, so I'm going to plug in 0 for t and 1200 for w. Remember, that's my initial condition, so I plugged it in down here in the same color. And just be careful here because you do need to solve for c. And even though the e to the 0.04 to the 0 comes out as 1, I still have that 300 I got to move over. So c comes out as 900, and then I'm able to get my final equation. What is the waste function in terms of time? It's 900 e to the 0.04t plus 300. Now, I mentioned the actual question is, well, how much waste is in there after time t, or after time 2 years? So I didn't have room to put it, so I just figured I'd show you the calculator input. So all I did was take that function, throw 2 in for the number of years, and it output 1,274.958 tons of waste. Remember on the AP exam, as I mentioned, they would have you round decimals to 3 places. So I would answer this as 1,274.948 tons of waste at 2 years. All right, so that's part A answered fully. Part B, just to remind you of it, was to use the tangent line approximation from t equals 0 to project to how much trash would be present after 3 months. Once again, we have the W function, but they don't want us to use it. They want us to use this tangent line approximation. So first thing I did was to make sure that I have everything in the right units. Waste is in tons and time is in years. So when they give me 3 months, I don't want to keep it as 3 months. Basically, how many months are in a year? 12. I have 3 out of the 12 months. 3 out of 12 is a quarter. So 3 months is a quarter year. So I have 0.25 for years. So I want to use that number, not the number 3 months. All right. So now knowing that, I'm going to make the tangent line approximation. I'm going to use point slope form as usually the best form in calculus used for a line. Now, point slope form is out of context. It's y minus y0 equals slope x minus x0. Now, x is the independent variable, so that's why I have t's in here. And w is the dependent variable, the output, that's the w's. So I wrote this in terms of the w's and t's, but this is point slope form of a line. Now, they want me to make the tangent line approximation from t equals 0. So over here, that's my initial condition. When t is 0, w is 1200. So at 0, that's t naught, or t sub 0, I get out w naught, which is 1200. So that's the point I'm using to make my tangent line approximation. The only thing that's left is to find the slope. Once I find the slope, I'll have my equation of that line. I can use it to project the value that I want. Now, what's the slope? Remember, the slope is the derivative. So I'm going to find that slope by using dw dt. Namely, I'm going to use dw dt at the spot I'm doing the tangent line approximation. So I want the derivative evaluated at 0, 1200. Once again, t0, w 1200. So I took those two values and plugged them into this equation. So this is the general derivative. And when I plugged it in, it's only in terms of w. So all I had to do was plug in the 1200. It doesn't have a t in it. So I plugged in the w and solved for what the slope is. Solving this equation, or I guess just calculating this number, gives me 36. So that's the slope. So once I knew that, I went back and plugged that in, and wrote the equation down here. So I get W minus 1200, 36 times T minus 0. So I just ditched the 0. Got this, for good measure, just moved the 1200 over. So now I have in slope-intercept form. W, according to this tangent line approximation, what is my amount of waste? It's approximated from time 0. It's 36 times whatever the new time is plus 1200. Remember, the time in years is 0.25, so calculating this with the 0.25, the quarter year plugged in, 3 months, gave me 1,209 tons of waste. So after a quarter of a year goes by, there's 9 more tons in there. There's now 1,209. Now, I realize this is an approximation. This is not the exact value, but it's very close, and I'll show it at the end. The exact value can be found by plugging into this. But I want to avoid showing the exact value because the next problem asks if this is an over or underestimate. Instead of just finding it from this formula, they asked me to use the second derivative. So I'd rather first show you how I'm going to figure out whether it's an over or underestimate, and then I'll verify that it truly is. So just to remind you of the last problem, it wants me to find the second derivative and then wants me to use information about the second derivative to see if that approximation was an over or underestimate. All right, so that's what I'll show on the board behind. So I reformulated the problem up top, so hopefully you don't have to keep going back and forth in the video. It wants me to find second derivative and tell whether my part B answer was over or under the real value. So finding the second derivative shouldn't be that bad because they gave me the first derivative. You just have to kind of follow this notation. So I have the first derivative in terms of W. Now, to get the second derivative, they want the second derivative in terms of T, with respect to T. So remember, d dt means I'm taking the derivative with respect to T again. So this is already the first derivative with respect to T. This is saying let's get the second derivative with respect to T. I'm going to do that on both sides. So I'm taking derivatives like an operation. I'm taking that operation on both sides. When I take the derivative of the derivative, I get the second derivative. So this is how it's notated. Remember, d squared w over dt squared. On the right side, I need to take the derivative with respect to t. The problem is there's no t's in this, so I have to remember to use the chain rule. When I take a derivative, this multiple comes along for the ride. So since this is being multiplied, this doesn't do anything. However, I need to take the derivative of this with respect to t. W's derivative is 1, but because it's with respect to t, I have to do the chain rule. So it's going to be 1 dw dt. The derivative of 300 is 0, so it goes away. So basically my second derivative is 0.04 times dw dt, the first derivative. Now I know what dw dt is because it's sitting right here. So I'm actually going to replace the first derivative with its expression up here. So instead of writing 0.04 times the first derivative, I'm going to write 0.04 times w minus 300. Now that simplifies a bit. I didn't multiply it all the way through, but combining those, I get 0.0016 times w minus 300. So this is my second derivative based on the first derivative. So notice that this is still based on w. Now, how does this get me information to answer what they want part B? How do I know whether it's an over or underestimate? So that work is on the right. I'll explain it if you don't follow it. The second derivative, I can actually evaluate it at 0.0 and use this to figure out what's always true about the second derivative. If I evaluate it at the 0.01200, the second derivative only needs me to plug in the w, because remember, it's based on just w. So if I plug in the 1200, it gives me the number 1.44. The key thing is not what the quantity actually is, but that the quantity is positive. Because what turns out to happen is, remember, the waste increases after this. The lowest it ever is 1,200, and then after that it keeps going up. So what that means for this equation is that since the 1,200 version was positive, in every number after that, all of the waste values after time 0 are bigger than this, that means this will always come out as a positive number. So I basically noticed that and wrote it, that this gives me enough information to know that the second derivative is always positive for all the t values where this thing is defined on that domain. So since the second derivative is always positive, we have to go back and remember what this means for functions. The second derivative being positive on this interval means that the function is concave up. Now, I make a conclusion from that, but I'll show you why why I'm able to make this conclusion. Because basically the AP will accept my answer, but you may find my answer unsatisfying. Because you might go, okay, well, why is that the case? So just realize I'm going to give my answer, and then I'll explain why it's the case. Since the second derivative has to always be positive based on the fact W is always 1200 or larger, and this thing can't ever come out negative. Since the second derivative is always positive, the function is always concave up. Now, I just wrote, since W is concave up on the entire interval, the answer from part B has to be an underestimate. Now, that's sufficient for them, but you might wonder, well, how am I supposed to know to write that, or why? So I'll show you a picture that justifies this thinking, and then actually show you it's true by using the function itself. All right, so why does a positive second derivative making it concave up give me that's the part B answer is an underestimate? Well, here's a picture of a possible scenario that's going on. It may not be exactly the picture, but the concept of it's good enough to explain what I want. So basically, when we do our tangent line approximation, think of the real function as this function. Now, I have the function curving upward because what I found from the second derivative is always positive. So the function's always concave up. So the real function is doing some kind of upward curvature. I made the tangent line approximation. The tangent line approximation uses the tangent line at 0 and shoots off along the tangent line instead of following the curve. If you're close by 0, there's very little difference between these. The farther you get from 0, the further apart these become and the worse the tangent line approximation is. So basically this line's representing the tangent line approximation from 0, where the curve is representing the real function. Now I exaggerated it. These would be pretty close, but I exaggerate to show you why it's an underestimate. The tangent line just goes straight out. Since the function is actually concave up, it has to curve up and away from the tangent line. So that's how I know the real value is above the estimated value, or rather, the estimated value is underneath. It's an underestimate of the real value. All right. Had the second derivative been negative, it means it would have been concave down, and it would have been the opposite. So that's why the AP allows you to just use the concavity to answer it. Basically, if it's concave up, it's curving higher than the line, so the line's an underestimate. If it's concave down, it would be curving below the line, and then the line would be an overestimate. So I don't have to explain all that on the exam, but that's the logic for you, so you know how to make your conclusion. Like I said, without the picture, you can just answer this. So now, hopefully, you know why. When the function's concave up, it's making my tangent line an underestimate. And just to verify that that is the case, we have the original function. So I could figure out what is the real value and then see if my estimate, remember my estimate was 1,209. So I'm going to go back to the calculator and just show you what the real value is. So using the function, make sure you can see that. So remember, before I plugged in time 2 to answer part A. The real value at 3 months would have me plug in 0.25, and notice it comes out as 1,209.045. The real value is a little bigger than 1,209. My tangent line approximation was close. It's only off by 0.045 roughly. But notice that it is true that my tangent line was an underestimate, because that curvature, it's curving up a little bit above the line, and it's causing it to gain that extra 0.045. All right, so all of this is consistent with itself. hopefully it makes sense. Like I said, this was based off of a real AP problem. It's not uncommon for them to kind of mix and match things from different parts of the course. So I thought this was a good problem because not only does it have a differential equations application, solving differential equation, but it has some good interpretations. It has you not only find the original function, but have you find a second derivative, and actually has you do some stuff with what they mean. All right, so that'll end this section on differential equation applications. And once again, this would have been my last lesson in general. I may or may not put out another lesson with any odds or ends that I may have forgotten. But overall, we should have everything we need overall to do their AP exam. As I get more information, I will release all of the topics that I know are on the exam and then the topics they took off. Of what I've taught, the topics I think that I've taught that have been removed, for sure, they did mention that they're not going to do integrals with velocity, acceleration, and position. So we were doing that right before we left. So unfortunately, they ditched that because I taught that, and now we don't need it. So far as I know, everything else I've taught is on the exam. Luckily, all the other topics that are on the exam I hadn't gotten to yet, and I skipped them to go ahead to this, what I would have done last, the differential equations. So overall, you should have pretty much the entire course. Like I said, if there's some little thing that I forgot, I'm going to go back through and make sure. Once I have everything situated, I will send out study guides and review sheets and things like that, catered to what you need to know. So I'll probably give you an outline of all the topics by unit and a formula sheet. Remember, they don't give you formulas, but things you can study. You'll have to study all those derivatives and antiderivatives and rules. There'll be the three theorems. The fourth big theorem they ended up getting rid of. So there were three big theorems: the intermediate value theorem, the mean value theorem, and the extreme value theorem. And as they start releasing problems on April 3rd, we'll go through them. I'll also start picking problems from AP Classroom that are free answer questions because they've unlocked them all. We can start doing those, and I'll try to, my future videos will probably be just showing you how to solve those problems. All right, so if you got any issues, be sure to let me know, but hopefully you're in a good spot now. So like I said, be in contact, and good luck going forward.